In the last 2 decades, active shooters and school shootings have risen to a distressing magnitude, to the point that the term school shooting now stands at the forefront of society's conscience. While police response time is 7 to 18 minutes, the bulk of the shots are fired within the first 5 minutes, during which time active shooters are able to wreak unimaginable havoc. Although law enforcement has worked tirelessly to abate these lagging response times, one harrowing fact still remains. Police simply cannot get to the scene of the crime fast enough.
In order to combat this issue, we have composed a team of 4 electrical engineers at Stevens Institute of Technology, with members specialized in both hardware and software problem solving, to form ASAP, Active Shooter Advanced Protection. We have worked diligently since the beginning of the semester and will continue until May 2019, at which point our project MVP will be completed.
Once a firearm is discharged, an array of microphones pick up the sound of the shot and triangulate the sound to within a few inches of accuracy. In order to reduce false positives, we'll utilize multiple different methods of discriminating the sound. Discrimination begins in the hardware accompanying the microphone. We have implemented a conditioning circuit to refine the audio input to allow for proper filtering and processing further on in the system. A 2 to 10 kHz bandpass filter serves as the first wall, eliminating most noise from human speech and any other high-frequency interference. The signal is further discriminated in hardware and software, which look for characteristic spikes and then employ the timing of those spikes to calculate the precise 3D location of the shot. Lastly, a trained machine learning script will characterize the audio event as either a shot or not a shot, amidst heavy noise or large attenuation. Once the sound and location of the shot are confirmed, camera vision and depth currently provided by the Microsoft Kinect acquire the body of the perpetrator and track him or her throughout the school. With the known position of the shot, the point cloud provided by a depth sensor will be employed to search for people in the area of the shot and probabilistically determine the perpetrator. The known figure of the perpetrator will then be linked to a face via facial detection, providing a vehicle for real-time tracking. Once the system has acquired the perpetrator's face, the system, in which all rooms are linked throughout the building, will hold and track the perpetrator's position, relaying real-time position to the proper authorities. To assure that the problem is resolved as fast as possible and without fail, law enforcement will receive the real-time display of the shooter's whereabouts, both in video feed and a floor layout display. This will decrease the time it takes for police to reach the shooter and increase officer safety by preventing surprises. All other students and faculty will be informed of the shooter's position and directed away from the shooter via an intuitive visual system, providing a safe means of escape for those locked out of the classroom. After the perpetrator has been acquired, an active deterrent will be deployed to slow or even halt him or her until law enforcement arrives. Currently, concepts include automated pepper spray, door locking based on perpetrator location, or loud disorienting sound. Overall, our system aims to halt the event immediately after the first shot and mitigate further injury or loss of life by providing crucial information to law enforcement students and faculty.
We are currently making do with 95-cent microphones, self-provided Arduinos, and Raspberry Pis, as well as resistors, capacitors, and amplifiers provided for free by the school. Moreover, much of our prototyping efforts have been slow-moving due to our lack of resources and prototyping supplies. With your help, we will be able to afford the tools necessary to vastly accelerate our development timeline and further improve the precision, accuracy, and reliability of our system. If granted the money, we have a clear plan on effectively using the funds as shown here in our estimated budget. The early stages of our system currently work to triangulate the sound of a clap, since clapping is much easier to reproduce than gunfire. The triangulation works well, but is inconsistent due to our current low-cost equipment. A graphic user interface displays the results of the triangulation algorithm, shown as a red dot in reference to the room, and the microphone locations, shown as blue dots. We also began work with the Microsoft Kinect, designing a crowd directioning system and designing an active deterrent system.
Although we have completed a lot, there is much more to complete in our future. From a hardware perspective, our current system is comprised of 3 prototype microphone circuits. This will eventually extend to 8 new and improved circuits, including efficient filtering and a hardware discriminator to determine the location of the shot. We also have to finish designing and fabricating a crowd directioning system and an active deterrent method. From a software perspective, we are on the verge of training our audio characterization script. We must assure the target is acquired through camera vision and hash out the real-time location tracking. Additionally, we must develop our graphical user interfaces to report instantaneous data to authorities.
We are attempting to solve a huge problem with limited time and resources. Although we work hard every week to produce results, we cannot accomplish this task alone. We need the financial aid and mentorship provided by Harris to attain our far-ranging aspirations. Feel free to view our website at the following link or QR code.